Today we're here to present our senior design project, which is a network-based lighting control system for energy efficiency. My name is Jason Victor. To my right is Cedric, Waku, Chong, Abdullah, Yousefi. Our advisor for this project was Dr. Ma. The heart of this project is energy efficiency. The data from the U.S. Department of Energy shows that lighting makes up 14% of energy consumed in commercial office spaces. We estimated with the implementation of our design that we can reduce this by at least 50%. This would transfer into major costs for companies. Now I'll just do a quick overview of the system design. We have a block diagram view of our system. Light sensor measures light, ambient light, and light from bulbs in our office space, produces an analog signal which is sent to a microcontroller. The onboard analog to DC to digital converter, 10-bit DC converter, produces a digital signal, digital value which can be used by a feedback control algorithm. The controller then outputs another value to an output port, which produces a pulse width modulated signal that has to be first filtered and then amplified before being sent to electronic ballast, which regulates the current flow in a fluorescent bulb. The components I just mentioned, minus the sensor, the ballast, and bulb, make up what we call the local control system. This picture is our LCS after integration. This second figure is a more detailed view of our system. Specifically, it shows the values of our resistors and capacitors. We have a low pass RC filter op amp, but notably on the bottom right, there's a computer connected to the microcontroller via a network. We call this our central control system, and this is how we control the system remotely. Using an Ethernet host shield, we're able to connect the microcontroller directly to the network. That's a picture of those two components. So we programmed the microcontroller as a web server. Using a browser and the IP address of the host shield, we can send HTTP requests to the microcontroller. This is first stored in a character, in a buffer, and then separated to get a command and parameters that's needed to service the request. After request is completed, the microcontroller will then send data back to the browser in form of HTML. And this screenshot is an example of what we'll get on the browser. In this particular case, we were trying to read the analog, the ADC value on the analog pin A0. If you look at the URL, that's actually the request that's going to go to the microcontroller. There's the IP address of the host shield. Analog read, which is the command, and 0 is the pin that we wish to read. Next, my colleague Cedric Waku is going to talk about some of the components in our team.
So, in our local control system, the first component we're going to talk about is the microcontroller. It shows the Arduino. That's 14 digital input-output pins, 6 analog input pins, and operates at clock speed of 16 megahertz. Next component is the low-pass filter. This filter converts the output PWM voltage from the microcontroller into the 0 to 5 volt DC output. Top, you can see VN, which has 5 volt peak to peak. At the bottom is the level output DC, 0 to 5 volt. Circuit value chosen for this circuit was 660 microfarad capacitor, and R value was 100 ohm. This output was doubled using the LM741 from 0 to 5 to 0 to 10 volts. And we achieved the gain of 2 using the equation of the non-inverting amplifier. RF and RG were chosen to be 100K ohms. And this voltage was used to operate the electronic balance. As you can see here, we have a gain of 2. I represents 0 to 255 duty cycle of the PWM coming from the microcontroller, and V from 0 to 10 volt is the output from the op amp. The electronic ballast Mark 7 by Philips controls this voltage from the op amp. We retrofitted it on the light fixture, and it is connected to a F32T8 fluorescent bulb. Testing were conducted on a tourniquet by varying the voltage from 0 to 10. A sweeping control from 2 to 8 correspond to a change from 10 to 170 lux. Finally, the light sensor. This is CES. It was donated by PLC Multipoint. It monitors ambient light and outputs the analog signal to the microcontroller. This plot represents the output of the sensor against the sample illuminance on the desk surface. We obtain a linear relationship as a result of testing this. The microcontroller converted the microcontroller does the analog converter to the output of the sensor. Next, Alan will talk about the PI controller.
All right, this is a basic block diagram of our entire system. Once the light sensor drives the voltage to the ADC converter, we get a value from 0 to 255, negative value. And that is compared to the set points by taking the negative value of from the ADC and adding it to the set point. The set point being a number from 0 to 255 that represents the desired lux, or I'm sorry, luminance on the desk surface. And the result of that is an error signal, E of t, that passes into the controller. The output of the controller, U of t, decides the duty cycle of the PWM signal that's fed to the RC filter and so on, that decides the relative light level that should be produced to keep that steady illuminance on the desk surface. And here at the bottom of the slide, we have the general equation we use for the controller, the PI controller, proportional and integrated controller, where we took the error, multiplied by a constant Kp, and we took the integral of that error over time, and multiplied it by a constant Ki, and received the controller output U of t. Okay, we use the PI controller, and here you see the basic algorithm for a microcontroller to output the control output. Here we have the error signal read on the first line. On the next line we have the integrative term, adding up all the errors. And the controller output is set to the equation, as I mentioned in the previous slide. And then we have the living functions. So in case of fluctuation, the control output decides to go below 0. We have a ceiling conditional here. And in the case that it wants to try to go above 255, we have a ceiling function. previous one is a floor function. And that control output is actually read to or sent to the port that delivers the PWM signal to the RC filter. And that is our PI controller. And Abdullah Yousefi will speak about the efficiency.
Hi everyone. I'll carry on with the system efficiency. To measure system efficiency, we consider three different scenarios. For case one, the system is off and no daylight enters the room. So we just measure the wattage in the fluorescent light bulbs if they're on 8 hours a day, Monday through Friday, throughout the year. And the cost of leaving it on for those operation hours would be $80. For scenario two, the system is on, but no daylight enters the room. And the desired lux level on the desk surface should be 500 lux. And our PI controller was set for 500 lux. But we measured if the lights are all fully on, 915 lux on the desk surface. So the PI controller needs to bring the wattage and the fluorescent lamps down to produce 500 lux on the desk surface. And the cost for this scenario would be $44, and the saving in comparison to case one would be $36. That would give 45% energy saving throughout the year. The last scenario, the system is on and daylight is entering the room. We took different samples for several days to see how much light entered the room on the desk surface to come up with an average daylight lux level. And our average was 235. And again, the desired set point for the desk surface is 500 lux, so we subtracted the 235 from the 500, and we were left with 265. That was how much wattage we needed in the fluorescent lamp to produce 265, the rest. And the cost for this scenario is $23, and the saving again in comparison to case one would be $57. That would give us 71% energy saving. Let's talk finances. The total cost for the project was $410. That's how much we spent on the project. I want to mention, as Cedric actually mentioned before, the photodiode light sensor was donated by PLC. The most expensive item we purchased was the Glimmering Galaxy, which was $137. And on the other side, we have actually how much it would cost to set up our system in one of the offices. It's $251. Within 6 years, it would the saving would pay for the cost, and after that would be just saving. And of course, it would be always saving on energy. These are the man hours. Total hours worked on the project was 689, starting from January 27th. And the specific contributions are listed of each individual team member. For lessons learned, we learned how to Arduino development, how to connect the microcontroller with the network and have data being passed back and forth. We learned how to implement the PID into the system, so it's running always in the background and keeping it at that set point. For team experience, we all were introduced to project design. As Dr. Pagos always mentioned, 493 is a bridge between the real world and university life. And of course, one thing we've learned was time management, how to manage our time and be always on time and finish the project. In conclusion, I want to mention that the project was a success. It reduces energy and it's cost effective. I would like to thank Dr. Mark, Dr. Cook, Professor Benny, and Dr. Packwood, and also Cynthia Valentine for allowing us to use the adjunct office for testing. And we have a quick demo to show. Any questions?
when you were discussing savings,